Okay, so I'm Blaine Lilly. I'm from Mechanical and Aerospace Engineering. My talk's going to be completely different. I'm not talking about any research I've been doing, really. I just want, my intent on coming today was to see if you folks a little sort of a primer on 3D, what the public calls 3D printing, engineers call it additive manufacturing, but also to give you an idea of what's available to you here at Ohio State, at least in the College of Engineering. Now, Dr. Dean is sitting out here in the second row, and he's in your college, and he's doing a lot of the same things. So he's another resource for you, but I'm going to specifically talk about what we're doing up in engineering. I thought since we started with the cartoon about thinking outside the box, we should end with one, you know. Not everybody thinks it's a good idea to think outside the box, right? So anyway, okay. So my background really is in manufacturing, and from that I got into product engineering. I see a few of my students out here in the audience. I teach a course in product engineering in mechanical engineering. I don't claim to be an expert in additive processing. This is something I've gotten into. I run the machine shops in our department, and so as we've added these technologies, this has become a responsibility of mine. And what we've been doing, I've had a couple of grad students working with me on this, is we have some pretty advanced machines now in mechanical engineering, and our research has been to try to push the envelope with those, figure out what they're capable of, both in terms of the strength of the components we can build and how small we can go with some of these things. So what I wanted to do is just show you folks, if you're thinking about using additive processes for a device that you're thinking about making, you should come and talk to us and we can help you out with that. So as I just said, 3D printing has really become one of these things the last 5 or 10 years. It's really taken off, okay? Well, as engineers, we refer to it as additive manufacturing rather than subtractive manufacturing, which is the typical way you start with a chunk of aluminum or tool steel or whatever, and you start carving away at it until you get to the final shape that you want. In this case, we're going to start with basically nothing, right, but a CAD file, and we build the component layer by layer in different materials, okay? Now, you might ask yourself, why now? Why is this so popular right now? I think one of the reasons is these technologies are not new. They've been around for 20 years or so, but what happened is the patents expired, okay? So some of these original patents have expired, and now you see an explosion of interest because different companies are now free to get into this field and exploit some of these technologies. Really, this all started about 30 years ago when Charles Hall was granted the original patent for a process called stereolithography. I'll explain that to you in just a second. But again, all these processes work basically the same way. They take a CAD model, they build it up one layer at a time, and the materials are different, the processes are slightly different, but the basic concept is the same, okay? So you have to start, if you want to do a 3D, I'll just go ahead and call it 3D printing. If you want to use this technology for something you're working on, what we need from you is a CAD model, okay, from SolidWorks, from Pro Engineer, from one of those programs, and it will export the file in what's called an STL format, okay? Charles Hall was actually the guy who came up with that file format, by the way. And so basically what that does is it takes the surface of your model and it sends it to us as just the surface. That's all we need, okay? And then our software, and every machine has the same kind of software, will then take this STL file and slice it, okay? And basically then from that we can start to build the thing a layer at a time. So this shows a part. I brought a couple of parts. They're over there on the side. This is one of the parts I brought with me. Basically, you see it here. We've oriented it on the platen. Okay, now the platen is just the base of the machine, and it will move along the Z direction, whereas the head is going to move in X and Y. Okay, so basically this is a very sophisticated XY plotter. That's one way of thinking about it. With a movable base, it can move in the third dimension. Okay, and so what it's going to do is it's going to build the first layer, then it's going to, the platen will drop a few thousandths of an inch. You build the second layer, it drops again, you build the third layer, and so on and so on. So when you look at these models, if you go over and look at what I brought today, you can see very clearly the layers, okay? So one of the things the industry is trying to do is get higher and higher resolution, okay? So we can build smaller and smaller features. Okay, So this just shows you we have the STL representation of the model, and then the software will slice it after the operator has oriented this thing on the platen, whatever it is you want to build. Now I can go into endless detail here about some of the decisions we have to make, but for today I just want to give you kind of an overview of this process, right? So in this case, we orient it like that. The operator decides how thick does he want the slices to be. Okay, if you want to really fine detail, we can go down to 5/1000ths, which is just a little bit thicker than the thickness of a sheet of paper, right? And build each slice at that level. We can do twice that. We can do 3 times that. Of course, if you're doing, for example, a rough prototype of a component, you might want to use fairly coarse slice thickness, right? It's going to save you a lot of money because if you come to see us, by the way, these processes are not cheap, as you might imagine. So one of the things we charge you for is material, right? The other thing we charge you for is the time. So if you start using very thin slices, you're doubling or tripling the amount of time it's going to take on the machine, okay? So that's what you get, and this just shows you a couple different slices from that one single model, right? And we can orient the direction in which we lay down in this case, we're laying down strings of plastic, okay, which I'll talk about in just a second, okay? Different, well, I'll get to that in just a second. Most of the machines we have on campus, we work strictly with plastic. Other processes work with metals, but I would say at this point, plastics are sort of in the lead there, okay? So, all right. The point is, and there's a lot of misconceptions about this technology right now. Okay, I had a friend who asked me a few weeks ago, can you rapid prototype me or 3D print a solar panel for me? Well, the answer is no, okay, because we can't there are a very limited set of materials right now, okay? What we can do is just about any geometry you can conceive of, okay? So the processes, you got to keep this in mind, the process is very good at doing very complex geometries that we can't do any other way, to be honest with you. But the material selection at this point in time is very limited. Now, there's a lot of research going on to expand that range of materials that are printable, okay? But right now, it's fairly limited, okay? All right, so all these processes use essentially the same method. First they deconstruct the CAD model, then they reconstruct the physical model, okay? And they differ in the materials and the processes. I want to just briefly mention 3 different kinds. So stereolithography was the original process. This used liquid photopolymers that would solidify when they were hit with a laser, okay, a UV laser. That process is still out there. 3D Systems owns this system, okay? Selective laser sintering is a process that uses metal powders. The word sintering actually is a misnomer. It's not a sintering process. Basically what you do is you melt the metal powder. The powder's rolled out one layer at a time. The laser strikes certain parts of it, melts the particles together, then another layer is laid down, the process repeats itself, okay? And then finally, fused deposition modeling, that's what we have in our lab. It extrudes a thin bead of molten polymer, okay? And basically, the polymer, as we get it, it's about the thickness of a strand of spaghetti. It goes through the extruding head, it's heated up, and then it's extruded through the head, and the printer, again, the printer head is moving in X and Y and lays down the layers, okay? Now this polymer, because when it comes out, it's about the viscosity of toothpaste, for example, it can't support itself. So if you have a structure that's got overhangs or needs support, our process will also extrude a support material. As it lays down the model material, it's also laying down support material. At the end, I've got a real short video I'll show you that makes this a lot more understandable. So this is just a representation of stereolithography. And you can see there, this is in a vat of liquid. Now, I'm not sure, and Dr. Dean may know more about this than I do, it wouldn't surprise me. These processes, to start off with, the liquids were quite hazardous, okay, toxic. And so this was not a process that you would, for example, want in your office or around students, for example, okay? So this process is still out there. In fact, one of the earlier speakers showed you some parts. I believe you were talking, yeah, you had the parts that were done by stereolithography, right? As far as I know, they're still fairly brittle. Is that true, would you say?
Generally, yes, but there are actually a number of materials that they use now. There's a couple pieces over here that are actually rubberized.
Oh, okay. All right. This shows you the selective laser sintering. Again, you've got a metal powder. In this case, you don't need a support material because the powder is laid down layer by layer, so the powder sort of supports itself as the part is formed, okay? And then this is fused deposition modeling, which we have. Again, we have these long strands of polymer. We have 4 different kinds of polymer right now. And along with that, you have the support material that's in a different head. And as the machine goes back and forth, of course, the software does all this for you. Once you orient the part on the platen and tell it what slice you want, the software does the rest of the thinking for you. And it will automatically generate the pattern to lay down the support material as you create your part, okay? So there are several of these machines around campus. The School of Architecture has one of the first FDM machines. First year engineering program just acquired a dozen MakerBots. MakerBots are very cheap, okay? The thing you have to keep in mind, there's a wide price range available on these machines right now. A lot of folks are buying these very cheap, low-end machines and assuming that they can build, you know, really high-end parts. That's not going to happen. One of the things that you'll notice, I'll show you a photograph of our machines here. These processes need to happen at an elevated temperature. MakerBot works at room temperature, okay? So it will build the little plastic part, but when it comes out, the bonding is not very good at all because it was done at ambient temperatures rather than at an elevated temperature. In mechanical engineering, we have 2 FDM machines. Our older machine is a dimension machine. It uses strictly ABS polymer. One of the earlier speakers was talking about ABS. ABS is a very tough engineering polymer, so you can build parts that will really take a beating. Okay, one of the reasons we've got 2 FDM machines is because in mechanical engineering, we build parts for the car projects. We build a lot of parts that are going to take a beating, so we want parts that can really stand up to some stress, okay? Our other machine, our new machine, is the Stratasys Fortis. This is pretty much a state-of-the-art for FDM machines. Stratasys is the company, by the way, that owns the patent on these processes, okay? It uses a variety of polymers. Right now, it can theoretically build parts out of 9 or 10 different polymers. When they sold us the machine, they gave us the software and the tips to do 4 of them. Each additional polymer costs us another $15,000. Okay, this has a pretty large build envelope, 16 by 14 by 16 inches. It's not the biggest machine they make, it's the second biggest, and it's a pretty capable machine. So that's the Fortis there on the left and a Dimension on the right. These are both in Scott Lab up the street here. Okay, as I just said, we're interested in building functional prototypes as well as just form prototypes. So this is why we went with FDM, so we can have relatively high strength materials at pretty close tolerances. Okay, so right now, when we're trying, we can build parts to a tolerance of 5/1000ths of an inch. Again, that's about the thickness of a sheet of paper. Okay, now the strength of these parts is not equivalent to, say, if you had an injection molded part out of the same material. They're roughly about 80%, okay? And we have a range of different polymers. ABS at the low end, polycarbonate. We have an ABS polycarbonate blend. By the way, polycarbonate is Lexan, okay? So it's a very tough polymer. And then Ultem, which is a high strength, high temperature polymer, it can maintain its strength up to 400 degrees F. So one of the reasons we got this is, again, because we do build parts for the Center for Automotive Research. So we wanted a process so that we could build parts for them and they can go bolt on to their engines and run them. Also, this process allows us to custom design the directions that we extrude the material in, which will greatly affect the strength of the parts. Okay, this is one of the areas we're doing a little research in. This is a master's thesis student just graduated last semester, and you can see that we get a wide range of strength depending on the direction we lay down the roads, the strands in. Okay, and this picture, the technician who works with me this morning brought this up to use my microscope to take pictures. So this is literally right off the press. But over there on the side, you see a piece of 5,000th shim stock, just to give you an idea. So this was, he's actually doing something for some folks over in food science. And what they're trying to do is determine the spatial sensitivity of the human tongue. Okay, now, why they're doing this, I have no idea. They didn't tell me. But what we've done so far is build tiny little letters of the alphabet for them. And then they put these on people's tongues and see if they can read the alphabet with their tongue. Okay? So quite interesting. Well, this is the latest thing they brought to us to see how close can we build parallel strips. And so you can see the gap there is on the order of 5/1000ths of an inch. Quite frankly, we were surprised we were able to do this. This is pretty much the state of the art as far as the FDM machine can go. Okay. Now, there are some disadvantages, of course, to this. There's a pretty limited range of polymers that are available. Stratasys seems to be, well, I should tell you, Stratasys has just bought another company, the company that builds the Objet printer. Okay, so it's another technology that's out there. We don't have, as far as I know, and Dr. Dean, you can correct me if I'm wrong, I don't believe there's an Objet machine on campus at this point. There are some Objet machines in Columbus. Okay, so some of the design firms have Objet machines. They do elastomeric materials, which is very interesting for some of you. And by the way, I should tell you, if you have a device and you're interested in this and you need some advice, please contact me. I'll be happy to send you to the people who can do what you need to do. I'm not in this for the money, of course. But so I do know some other things that are around town that maybe can be of help to you. So there's limits on the minimum layer thickness. The resolution is currently 1/1000th of an inch. The other thing about the FDM technology is the parts are quite porous. Okay, so that part that I had on the screen there a minute ago and sitting over there was for a turbocharger, right? Well, these parts right out of the machine are very porous. They can't hold a vacuum. They can't hold pressure. So one of the things we've been looking at is how can we impregnate these parts with, say, an epoxy or something like that so that they can hold high pressure or hold a vacuum. We're still looking at that, okay? And again, it requires a second material to be extruded along with the build material to support the structure as it solidifies, okay? So just to show you, I'm going to conclude here with a few parts and then we'll get on to the snacks. This is something that Kevin Wolff, my technician, just saw on the web, decided this looked pretty cool, and he decided to see if we could make it. So he made this last week. I brought this, that's sitting over there. This is I brought this with me. This is a bacterial swab that Dr. Das, and actually I haven't met Dr. Das, but Kevin tells me the idea was that they wanted to put this is a nasal swab, and you want to protect the inside of it while you're inserting it because you want to get the bacteria at the back of the nose, not at the front of the nose. And basically what this thing does, we build it like this. Okay, so it can move, one part moves relative to the other, so the swab's inside and it's got the shield around it. Well, I can't think of another process, and I'm an old tool and die maker, so I know something about manufacturing, and I can't think of another way that you would do this and build this as one piece. Okay, so there's that. We've done some work with some of your microsurgeons, some of your transplant surgeons down here, Dr. Whitson, Dr. Black, who are doing some transplanting rat kidneys, and so or livers rather, and we worked with them on some microsurgical tools. This is about the smallest we've gone with our process. And then a couple years ago, Dr. Sutradhar, who I'm not sure if he's still here or not, was in plastic surgery, working with cancer patients that the bone cancer had eaten away some of the support structures for the face, and he was rebuilding the faces. So I brought one of the skulls with me. The idea was that he would send us the MRI file, and then from that, we would actually build a full-scale replica of the patient's skull, the real skull, okay, so that Dr. Sutradhar then could build the prosthesis for it offline, and when he went in the OR, it was ready to go, and he could fit right into the patient, okay, which saved, of course, a lot of time in the operating room, okay? So those are some of the things we've done I think are some of the more interesting ones. Let's see if this video will play. I've been struggling with this all day. This is something OSU did for us. It doesn't look, well, there was no sound with it anyway, so just music. But you can see here, so just imagine your favorite tune playing in the background. Okay, but this is why I want you to see. You can see the two heads there, and so it's going back and forth. It builds the structure, and then it builds the support material right beside it. Okay, this is kind of a student created this chess piece that was sort of interesting looking. So the folks from on campus made this video, and they liked this chess piece, so that's what they did the video of. And a part like this would take, just if you're interested, maybe 40 minutes, something like that. And then, of course, we have to take it out and remove the support material from the build material, and then you're done. Okay? So there you are. Okay? So again, our machines are available. If you're interested, come and see me. Again, the cost is based on the kind of material you want. Ultim will cost you twice as much as ABS. It's an expensive polymer. There's our contact information, and I'm down there. For you doctors, just remember I'm distantly related to Eli, okay, over in Indianapolis. So you can remember my last name. Unfortunately, they have all the money. Any questions? Thank you.